So I start second day. Good morning, everybody. So today, the main idea of the lecture today is to show, to demonstrate how several characteristics of linear stationary system can be represented as LMI. So let me recall some definitions. So consider a linear system. Initial conditions are fixed or given. And we have also, it can be treated like output, but this is, it's like desired characteristic of the linear system. Maybe output, if you wish to consider it. So it's a function of state and functions the same external entrance. W may be considered like control, but maybe also considered like noise. So this is external signal for the system. So we consider that this system is controllable. You know that system is controllable. Equivalently, it can be expressed like controllability Gramian strictly positive. This matrix integrable in time from 0 up to infinity, strictly positive. It's only I recommend you. I would like only to recall you these definitions. Transfer function of this system evidently is from x to z. You should take a Laplace transformation and you obtain transfer function like this. This is transfer function of the system. S is complex variable from complex space itself. Several characteristics of accepted now in modern control theory. So H infinity norm of some transfer function is defined like that. This is only definition. When we introduce definition here, no place for discussion, it's definition. So only a special notation here, X star, it is conjugated matrix to H. What does it mean? It is transposed and imaginary part contains minus. This is short definition, not to write so complex. This is conjugated matrix H. It's possible to prove that if matrix D, return back, if our measurable or desired output does not contain elements of inputs, if D is 0, so in this case it's possible to easy to check that if this matrix is 0, so this norm is fine. And it can be calculated like this. It's possible to show. You can believe, I will not prove it, but it's possible to calculate the following manner. Matrix C, Gramian, and trace. So, if matrix C is a function of other matrix, maybe when we deal with feedback and Guy's gain of feedback or something like this. So if this matrix C in the output is a function of some other matrix K, so the problem exists, a problem. How to find this if matrix K to satisfy the following conditions that H2 norm of transfer function was less than some given level, tolerance level. It's easy. it's easy to understand that this representation can be rewritten in the following form. This is matrix representation of this for some matrix Q which trace less than 0. So first we dominated from above this matrix. We dominate by matrix Q minus 1, this minus 2, and then represent if this estimate is true for trace Q, so it will be valid for this matrix, and we obtain the following representation of this problem. But I recall that again by sure complement, this inequality can be represented in this form, and we have, in fact, the problem of describing of all matrix A satisfying this inequality is equivalent joint combination of two matrix inequality. One is this one. Trace is a linear operator, so it's also a linear function. And this inequality, okay, okay, and this inequality contains interdiagonal matrix C, but matrix C is a linear one, so we obtain LMI. So problem of estimation with given tolerant levels of H to norm in system which contains the free parameters also can be represented by LMI. Now, some definitions related with passivity. So by definition, system is called passive if the following condition fulfilled for all T. It means if you divide it here on T, on upper limit, nothing changed. So it means that the average, can be considered like energy of the output. So the energy 1/2, it's like power, no? Not energy, like power. So if this product more than 0 for LT, for 0 initial conditions, this system has a name, it's basic. Physically, it corresponds situation when, for example, in electrical circuits, we don't have some elements, some batteries, some energy inputs. So the question is how to check if some system is passive or not. Because if system is passive, exists a special exists a special methods simplifying the analysis of such system. Okay. This is time definition. In time variables, this is definition of passivity. But it's possible to show that this definition is equivalent to the following definition in frequency space. So if you have matrix H as a transfer function, so the passivity, this condition will be fulfilled if and only if the following summation of matrix plus its adjoint matrix will be positive for all arguments which belong to right-hand side of the complex plane. This property, because each matrix H can be represented a real part plus imaginary part. Now you can see when we obtain summation, imaginary part will be concealed, and we obtain only this expression. He will keep only real part twice real part. So this condition exactly equal to the following statement that if system is passive, is real part of transfer function is strictly positive. So this property is known like real positiveness of the system. So exists a generalization of this method. It related with definition of dissipativity. If before in the right-hand side we had 0, so this parameter eta is 0, so dissipativity, eta is index of dissipativity. So what does it mean? If we again divide it on t, it means that right-hand side it's power of input, and this is like the power of output, can be interpreted like power of output. So it means that power, if our signal passes through linear system, then the power of output less, at a time less than power of input. So we have decreasing of energy, or decreasing of power, so the system has a name dissipativity. So eta is index dissipativity. So if dissipativity is 0, we have passivity, but not inverse. If system passive, not obligatory, it's dissipative. So it's some definition I only recall you. So now let's try to verify which condition should satisfy parameters of linear system A, B, C, D to guarantee that some property of dissipativity, a partial case when eta is 0 of passivity fulfilled. So to find condition and express it, not so, how to say, because by definition, for engineer, for example, it's difficult to check y integral of product, of output, input, positive, it's difficult for any day. Or also, you should find the matrix H plus matrix H to take the real part and to check when it is, it will be positive for all arguments in the right-hand side of complex space. It's also difficult because you should check it for right-hand side if we will consider argument like real part plus G omega complex part. For all real part, it's not simple task. It's very difficult. You have some matrix and obtain when this is will be when the real part will be positive for all arguments. It's very difficult. But LMI help us to realize this analysis only using only one inequality. So, what is the technique how to analyze this? Now, suppose that some function where its quadratic function on x with some positive matrix satisfies the following inequality for any t. W its input, z is output, eta w, w t. So suppose that exists function w which satisfies this condition. Now let's integrate this function. We integrate this function. And if we integrate, we obtain v in point xt minus v in point x0. But you remember that we consider x0 equals 0, and that's why function v at point x0, when x0 is 0. So here disappears initial condition. And we have this v of x, integral of this, less than 0. If some inequality fulfilled is negative for all t, the same summation, integral is summation of negative is also negative. So we have this expression. But we can rewrite it in the following way. No, if p is positive definite, it means that this quadratic form more or equals than 0. So this function more or equals than 0, we estimated it from above. We take this integral right-hand side and this integral right-hand side with minus. So we have these estimations. We have exactly this one. But v is strictly positive. So it means that this more than this. You can take this left-hand side. So this is exactly dissipation property with index eta. So existence of some function of quadratic type for which satisfies this inequality exactly corresponds to dissipativity property. But what to do after? So we can let's calculate derivative of function value. Now this is like that because P is symmetric. In general, it's only for students and comments. That if we need calculate derivative, of quadratic function, of this function by x, when I is not symmetric, any matrix, so it will be like that. But if I is symmetric, we have two matrices. So here we exactly use this property. So to calculate derivative in trajectory of our linear system, this derivative has a name. It's Lie derivative of Lie. So if we calculate Lie derivative or direct derivative on this function on trajectory of our system, first we should calculate derivative with respect to x, and after multiply by x point, like a complex function. So derivative is this one. Then we substitute dynamic is here. And you see, we here have two variables. We have output and we have input. So this identity, and we can represent, we open bracket and we will have this expression for x, and we will have this mixed form. It's not this quadratic form, but this is not quadratic form. It's mixed with respect to x, w. Is symmetric part is here. Z is here, is given here. So substitution, return back. We have this expression. So instead of w, we will substitute the last expression we obtained. But here also exists z. So instead of z, we will substitute the definition. If we substitute all of them, we exclude z from consideration, and this inequality, which before was considered this inequality, can be represented as quadratic form with respect to which variables? X and w. And this is quadratic form. Exactly quadratic form. Symmetric, because this is a symmetric form. So before we prove that if some differential inequality with respect to w, if this inequality fulfilled, then immediately follows that our system is dissipative with index eta. Eta participate here. So, but this will be fulfilled. Is this Riemann fulfilled? Look, this is quadratic form and should be fulfilled for any argument. Argument is extended argument, x and w. So if this matrix negative definite, if this matrix is negative definite, then we can guarantee that our system is eta dissipative. So the first exactly here. Not negative. Here we see negative. It's negative if I put here minus, multiply and minus, it will be positive. So this is with minus. It is the same. So if this matrix is positive definite, for some, if if for our system, linear system with parameters A, B, C, and D exist positive definite matrix P more than 0, which satisfy this inequality, then our system, linear system, is eta-dissipating. So to check it, it's very easy to use a program from MATLAB, YALMIP or Sedumi, and put only your matrices, given your matrices, put this level of dissipation level, and program say, yes, exit solution. It's not important which matrix P you have. If exit solution, matrix is dissipated. But we interesting to find maximum dissipation level. What to do? You should make a cycle, a numerical cycle. Select, for example, we can start with eta equals 0, only to check passivity. If exist solution, then take a little bit more. We take eta 0.1, for example. Again, check this program, and finally we obtain, we may increase eta, and in final moment, program say, no solution. So return back one step before, and this is maximal dissipation level which you can obtain. So this is analysis which we can do. But look, here idea is demonstrate that LMI help to check very complex condition, because condition before you should verify real positivity of take real part of transverse function and check if this function positive definite for all arguments. It's not one inequality, it's infinitely many inequalities. But LMI permits to simplify this process, and only this very simple expression, you check it numerically in MATLAB, and that's all what you need to do. Certainly, analytical solution we cannot give, but this is practical analytical solution. So if exists any matrix P, positive definite, such that for given parameters of linear system, this inequality valid for given level eta, so the system is eta dissipating. Okay, so it's sufficiently clear. Next, it has a name positive real lemma. So in literature, before LMI, when appears LMIs, analysis of LMIs appears after works of Nemirovsky, Nesterov, and more or less it was in the 80s. Before, the condition of eta dissipativity also was formulated, but a little bit in another form. And another formulation of the same fact is this: it is historically 10 years before appears in literature, or 15 years before. So if for some eta, the following Riccati equation, why Riccati? Because this term is quadratic with respect to P is quadratic. If the following Riccati equation has a solution, then the system is, if this inequality is feasible, then the system, considered system, is L dissipative with some additional assumption. Look, but this is, it was old formulation. It was old formulation given by who considers it also Kalman, also Yakubovich considers this expression. But if you rewrite this formula, if you open brackets with respect to P, or no, only directly, if you, for this inequality, you wish to represent it using the, so you can see that this is exactly, this is S11, this is S22 minus 1, and this is diagonal element, This is exactly representation, sure representation of the previous estimate. Look, it is absolutely the same. This is which we obtain very easy, and this recurrent equation absolutely analog of the previous one. So, but if you try to find how to prove this original statement using the recurrent equation, it's very long proof, maybe 5 pages, 6 pages of the book you can find, or in the paper. But we obtained it in only one step using LMI. And this is the same. It was altered formulation, and we formulated a new version of this theory using LMI. Now, the same, absolutely the same idea, how to study, to check if our system is non-expensive. What does it mean, non-expensive? Again, divided by T, we obtain here power of output and power of input. So if power of signal in the output less than power of signal in the output, the system has a name non-expensive. So also it's possible using Parseval identity. It's not difficult. I only omit this. It's possible to show that this condition written in time domain can be rewritten in for stationary system, sure. Can be rewritten in equivalently, can be rewritten in frequency domain, like this inequality. But this inequality should be fulfilled again for all arguments. It's not simple to verify. It should be satisfy this inequality for all argument in right-hand side of complex plane. So this is two equivalent definitions. So in time domain and frequency domain. But how to check it? Now we show by the same procedure we can represent this condition like LMI. It's very simple. Okay, look. If we introduce definition H infinity norm, by definition it's very simple construction. You consider this matrix, which here in left hand side. This matrix is symmetric by its definition because it's transposed. And eigenvalues of this matrix all real, not exist complex values because of symmetricity. This is Hermitian form. We can say this is Hermitian matrix. In the case of complex symmetric matrix, it has a name Hermitian matrix. So lambda, we need to calculate lambda maximum. It will be function of argument. And if we take supremum maximum for all arguments in the right hand side, this is definition of H infinity now. But sure, I forget here square. Here should be root square because this is a square. And this I forget here square. Here should be square. So supremum, it can be rewritten like this. So it's possible to show that this extremum always will be obtained, will be reached in imaginary axis. Exists a Riordan lemma about this. So this extremum can be, we can only check not all right-hand side. We can only check on the boundary in imaginary axis. So E omega, we substitute imaginary axis E omega, and this omega, we should check this this definition to obtain a value of H infinity norm. We should check this supremum maximum eigenvalue in all imaginary axes, changing omega from minus infinity to plus infinity. The problem sufficiently difficult. Huh? But we will, so we need recall that this condition, if it is true for all S, I can take lambda maximum both sides, lambda maximum here and lambda maximum here. Lambda maximum is 1, taking supremum, and we can rewrite this condition for given initially in frequency space. In this form, there's h infinity less than 1. So if h infinity of some transfer function less than 1, then the system is non-expansive. But how to do that? It's not a simple task. Okay, again, let exist, suppose it exists some function, quadratic function with positive matrix P, which satisfies this inequality. Before it was Z, but now Z square and W square. Suppose that exists this function which satisfies this inequality for all t. If it is, again, considering zero initial condition equals 0, integrating, we obtain this inequality, absolutely the same. But V not negative, so V more than 0, and this is right-hand side from plus, and the right-hand side from right. So we have this inequality, that this integral more than this integral, put left-hand side, we exactly obtain non-expansivity property. It is the same approach. So if this condition fulfilled, if exists such quadratic function for any pair, no important which pair, if exists such quadratic form which derivative, Lie derivative satisfies this inequality, so then this system non-expansive. And now absolutely the same situation. Calculate Lie derivative on trajectories of our system. It will be this expression, substitute dynamic, again obtains the same expression, and recall that Z is the output or measurable output or desired output is a linear combination of the W. Substitute this Z. Look, we need substitute this Z here. Here, quadratic, we substitute it here. Open brackets. It's very simple exercise here. And we obtain again quadratic form which should be fulfilled. So this, the condition given in differential form will be written like a quadratic form of that expression with respect to extended vector x and w. Look, but it means exactly that this matrix negative definite. If I multiply all elements by -1, I obtain that this matrix should be positive, non-negative definite, positive definite. So look, what's interesting difference? Because here we have only one matrix inequality, And to check initially H infinity norm less than 1, as you know, we should calculate lambda maximum of quadratic Hermitian matrix over the whole imaginary axis for any omega. It's difficult, or it's impossible to check. But LMI help us to do that. So we can say that if exists matrix B positive, any matrix B, which such that this inequality fulfilled, so then our system is linearly, our linear stationary system is non-expansive. Now, if we consider additional requirement, it's not so restrictive, and we try find some papers related to the same property, but this papers written 10 years, 15 years before LMIs, you can find this condition. Again, if some Riccati equation fulfilled, it's like a lemma of Yakubovich and Kalman, they studied this.
Stop here. Electricity is not there.
Okay.
UPS is there.
So I finished exactly in this place. we will stop by technical reasons. So before, this condition was expressed like Riccati equation. But we know if we can see when this Riccati equation, this exactly is sure complement of the matrix which we obtain. So this is two equivalent representation, but certainly LMI representation is much adequate, much simple than previous one. So I don't know. We stop now,
No, we
or
stop now.
let's wait a little bit, no?
Wait a little.
Okay. So, as I show that all the results expressed property of non-expansivity given in form of Riccati-Levier equation. Now it's absolutely by sure complement. It can be, this is S11, this is S22, and this is C, which in diagonal. So if we return back, look, it is exactly this expression which what we have. This one, this invertible. So we obtains a very simple proof of checking the property of non-expansivity, which before it was not so simple. So this is only idea to how to demonstrate the usefulness of LMI. Now the condition before we consider situation when non-expansivity, we consider we check the condition when H infinity norm less than 1. How to generalize this approach for gamma for any positive value? Now it is evident if we divided this transfer function in gamma, we obtain the same, absolutely the same problem like before. So in this case, when we divided gamma, if we divided H by gamma, so we should divide first element and second element. The first element is sufficient to divide only C by gamma, and second element divide D by gamma, and apply the previous inequality when instead of C we will use C wave, and instead of D we will use D wave. And in this case, we can guarantee the tolerance level for H infinity equal gamma, not equal 1. So this is exactly the previous representation, and when we substitute values gamma, we will have this. Now here, so for simplicity, we can multiply this inequality by gamma square, because here appears -2 by gamma square, and it will be in this representation. So this is a very simple property how to check if H infinity norm of some transfer function less than some tolerance level. And it helps us to obtain estimation of H infinity norm. So we can again repeat iterative procedure for LMIs. First, we take large enough gamma. We use an LMI, we use LMI or Sedumi, and program say, okay, solution exists. Then we decrease gamma, again repeat, then decrease gamma, and finally when we obtain some value, and program say, no exists solution. We return one step back, and this is exactly tolerance level estimation of H infinity norm. So to estimate H infinity norm, you need to use the same procedure like for non-expansivity problems. So this is a very simple idea. For morning session for today, we have only 10 minutes, and after we finish. Next, we start at 4. So exists also definition of gamma entropy of linear system. The gamma entropy has the following. It's only definition without discussion. Why it's necessary to introduce this characteristic? Now here exists a matrix gamma. The matrix gamma participate, and it's possible to show that if parameter gamma tend to infinity, the value of this gamma entropy tends to norm of H infinity. So when H infinity start to be designed in 80s, element still not appears, and people to calculate H infinity numerically, people use this one. So they consider, because this is easy to, this is integral. Look, this is only one value. It's not necessary to check for all omega from minus infinity to this is an integral. There's only one value, integral characteristics. So it's possible to check, and after increase gamma, more, and we obtain H infinity norm. It was old technique how to calculate H infinity norm, but now we know that it's very simple. It's only iterative procedure for LMI expression. Now, how calculate this? No, it is. It's easy. Not easy. There's some theory, some part of H infinity theory. It's possible that this entropy norm can be expressed by trace of this product, where P satisfies this Lyapunov matrix equation. It's linear equation with respect to P. It's not. No, this is Riccati because this is square. Yeah, again the Riccati equation. It's possible to show that if for some matrix P, if some matrix P satisfies this condition, then this norm exactly equal to that. It's some part of H infinity theory. I have no time to explain why, but you can find it in a book of Zhu and Doyle. Doyle and Zhu, for example, they have a book like this. It's not easy to read, but this, you can find this property. Now, again, if you introduce some level lambda, so because this function, look, it's not simple to calculate. If you introduce upper estimate of lambda for this expression like this, a trace is a linear operator. So this is a linear inequality with respect to P. It is given like that. And if you consider this expression, changing it to minus, you remember my first comment when we start to study LMIs, that if you have equality, we can introduce a small q and consider it like inequality. So this we can introduce some small regularizer and we can obtain this inequality. So we will have two inequalities, one and another one, this one. So to calculate this norm or value of gamma entropy functional, we need select lambda, and again to arrange the iterative process, take lambda large enough. If it is solution like the smaller, up to the moment when we have no solution. Maybe this is the last for now the last expression. Suppose that we have a time delay system. Very simple expression. Linear time delay system. Stationary, it means that parameters A are A constant. Here we don't need to apply Laplace transformation, because when you will apply Laplace transformation for time delay variable, you know that the P is exponent minus 2, it is impossible to analyze. So let's introduce a function. Before we introduce only quadratic function, normally it has a name Lyapunov function. But now let's introduce Lyapunov-Krasovsky function. It contains integral from t minus tau e. Tau e is this time delay up to t, another quadratic forms, and summation. So we have several quadratic forms. We have one quadratic form here and L quadratic form here. So L plus one quadratic forms. Let's introduce this expression. Now it's evident that if the following property, if Lie derivative or derivative on trajectory of the system of this functional less than 0, we have asymptotic stability. Why? Because if all matrix is positive definite, so this function has 0 value when this 0 and other 0. So you have stability in origin of the system. So if this property fulfilled, our system is stable, asymptotically stable, between states and 0 and infinity. But asymptotically stable in global sense, because you know that in your course you studies, and we speak about Lyapunov stability. Lyapunov stability only in small origin. But here we speak about global stability. So we need to check. Oh, sorry. We need to. We need to check only this property that this system decrease. Value of A decrease always monotonically decrease over the trajectories. How to do that? No, we only should calculate it. We substitute. We consider this. Calculate derivative. It's easy to calculate derivative of this part because depends here depends on there only in upper limit and down limit. So we will have to when you calculate derivative with respect to upper limit, you obtain exactly subintegral expression in time t. When you calculate derivative with down index, it will be with minus the same subintegral expression time t minus t. If you substitute it, all of this calculate. If you substitute it, it's possible to represent right-hand side also like quadratic form. But quadratic form with respect to what? With respect to various variables. Before, you remember, we considered quadratic form with respect to x and w. But here, we have no w. We have these values like w. So, if we consider this extended vector, L plus 1 coordinates, so, and define this vector letter y. So this derivative exactly, there's no inequality, this exactly calculated. So we can calculate quadratic form with these matrices. So theorem is following. If this matrix, if exist positive definite matrices P and P such that for given stationary time delay system with parameter A, A1, A2, and so on, if this matrix negative definite, so our time delay system is stable. It's very, very simple. So I guess I can finish because that's this hybrid system. Okay, if we have time now, still. Or it's better finish. And how are you?
What audience is?
Okay, so we can continue. Okay, so only one slide more. Let us consider the so-called hybrid system. It's a hybrid system. What is a hybrid system? It's a system when, for dynamics of some equation, we use differential equation, differential models, and the rest of variables, it's algebraic relation. Look, so here this derivative, we separate vectors of states into one part is given by ordinary differential equation by ODE, and rest of variables it's only relation between them. It's also time delay system. It's also time delay model by hybrid time delay model. So another interpretation. Look, I can take this variable from right hand side with minus, and here put second derivative multiplied by parameter epsilon. If this epsilon 0, I obtain this. So in interpretation with when x in the right hand side, and instead of this I use x point epsilon, it's like singular equations. So, but we will not use it. It's only some association. So we have this expression. The definition, the name of this system is hybrid time delay linear system, also stationary system with constant parameters. How to study the stability of the system? So absolutely the same idea. We consider Lyapunov-Krasovsky functional, but here we consider two matrices, P and S. Here we have only one term of delay. So it's possible extend to multiple time delays, but here for simplicity I consider this expression. So we consider the Lyapunov-Krasovsky functional. Why this is functional? Because this is a function of x, and this is not function of x, it's function of all x inside of interval. So relation between some vector and some another vector has a name, it's function, but relation when you have some function, because this is a function given an interval, relation between function in some point has a name function. So this is not function, it's function of Lyapunov-Krasovsky. So we introduce this new functional and calculating derivative exactly, no inequalities, exact calculation derivative of this function. Again, taking derivative with respect to upper limit and down limit. So we obtain this and introduce extended value z with this, and we obtain quadratic form. If you will look, we obtain this, and evidently that if w less than 0, it's very simple analysis. We obtain asymptotic stability for this hybrid system. So it's very, very, very simple construction. Again, LMIs help a lot. So if exists solution of the, now we should find solution of two matrices P and S. If exist, so our system is asymptotically stable globally. No, I guess that's all for now, and we will continue it for. Professor Day, he will have my USB with memory, so he have it. And after you can take all my presentation for all 5 days. He will have it. Or if you wish, you can put it in, how would say, in some link of your department, and everybody will take it when they wish. It depends. So up to 4. Thank you.